Okay? So we've got our electrophile summary, all of the individual reagents that we could potentially use. Please note, and that's all the stuff in red, please note that 2 of those can have a lot of different possible combinations. I can do a lot of different carbon chlorides or alkyl chlorides, and I can do a lot of different acyl chlorides. I can change what's attached to that carbon here, and I can change what's attached to the carbons out here as well. Okay, so we get effectively an infinite amount of possible options coming out of those tail ends. Okay. The next thing that we didn't address is, now that we've got these functional groups, what can we potentially do with them? Well, for one thing that's not on this list, this guy in the middle, what did we say we could do with that?
Reverse.
We can run the reverse reaction. Okay, how do we run the reverse? We use dilute H2SO4. Okay. Once we form the nitro, okay, that nitrogen, okay, has a bunch of oxygens bound to it. Can we potentially change that in some type of reaction? We could reduce it. We can remove oxygen bonds and add hydrogen bonds. In the process of doing so, we now end up with an amine, the NH2. Okay, how do we do that? We need a particular catalyst and reagents to do that. Those reagents are specified there. Okay, you don't need to know how that works. You just need to know that it does work. Okay? Why is that one a particularly interesting reaction to do? Where does the nitro direct? Meta. Where's the amine direct? Orthopara. So we can put a nitro onto our ring, reduce it, and now if we try to put another substituent on the ring, it's going to go to a different position. Okay? So we can actually start to shift around and start to play with what positions we want individual groups relative to our substituents that are there. Okay? Once we've got the CH3 on there, what can you tell me is special about that carbon? Carries a particular name. It's known as benzylic. What chemistry is available to benzylic carbons? We've got our radical mechanisms. We can do a substitution reaction. We can trade a hydrogen for a bromine. They decided to add a ridiculous amount of bromine to it so that you fully substitute all of the hydrogens off, but we could have done that one step at a time. If I just want a bromine on that carbon, NBS. There we go. And I've now substituted a hydrogen for a bromine. Yes. What else could we do with the benzylic position? Well, as long as there's hydrogens attached to it, we can oxidize it. We could add our permanganate and permanganate and our hydroxide, followed up with acid, and we can put on our carboxylic acid. Is there another reagent that we could have used in that position? PCC won't do it. PCC reacts with alcohols. There's no alcohol there, but you got the right idea. What was your choice? Yeah, we can use our chromic acid. Okay, why would we pick permanganate over chromic acid? What was that movie with Julia Roberts in it? I know, that narrows it down. With all the poisonous stuff, she's a lawyer or a paralegal. Erin Brockovich. What was she chasing down? Anybody saw that? She was chasing down the presence of a particular metal ion. That metal ion was chromium-6. Guess what metal ion is in chromic acid? Chromium-6. So why do we not use chromic acid typically? It's really, really toxic. Okay. So in most cases we might use, or we'd probably use the permanganate option. The last thing that we could go through and do, it's another one of those you just need to know it. With that carbonyl functional group, we've got that carbon and oxygen bond, very much the same as we had our nitrogen-oxygen bond. What can we do with oxygen bonds? We can reduce them. So we can reduce the carbonyl down to just the alkyl portion. All right, to do that, again, you just need to know the reagents. You can use that reagent to go through and do that reduction. Okay? Why would we do that? Why put on an acyl group to only turn it into a carbon chain? Because why didn't we just do the carbon chain to begin with and do the Friedel-Crafts alkylation instead of the Friedel-Crafts acylation?
Carbon-carbon bonds hard to form.
Both of them will form that carbon-carbon bond. What's the issue with the Friedel-Crafts alkylation? It needs an activated ring. What if your ring is deactivated? You can't do the Friedel-Crafts alkylation. So what would you have to do instead? The Friedel-Crafts acylation. But if you want the carbon chain, how do you get rid of the carbon or that carbonyl? You reduce it with that reagent. Okay? So we'd have to follow different paths to do different things. It just ultimately you have to be aware of what's happening in each case. Okay? So the sneaky chemistry is what I'm addressing at that bottom, is all the stuff in blue. Okay, almost. We haven't addressed that guy yet. So we can convert our substituents around, and then between alkylation versus acylation. We can acylate something, then make it look like we alkylated it, okay, by doing that reduction. And that's really just going to depend on what your starting material is. If your starting material is a deactivated ring, you're going to need to acylate. You can't alkylate. Okay? Last thing I kind of want to throw in there is beware of your sneaky chemistry. What can you tell me about that amine? Give you a big hint. Are we going to get a bigger hint? What's special about that lone pair? Could go into the ring. It is partially negative. What other things can partially negative species do? They could react with acids. What happens if the amine reacts with an acid? What does that group become? I don't have a, whoa, that was supposed to be an eraser first. What was that? Close. Ammonia is NH3. This isn't officially NH3. It's NH3 bound to something else. It's NH3 plus. Ammonium. Okay, it's an ammonium ion. Why is that important? Ammonia, or NH2, directs to what position? Our para and ortho positions. If we follow through and do our conversion, what happens? Now it shifts to the meta positions. So we have to be aware that acid-base chemistry can come in and mess with the chemistry of an amine, okay, and potentially increase the likelihood that we see odd substitution patterns. Okay, so you got to watch out for that. Okay, so those are all of your electrophiles. The big summary that we kind of talked about. Okay, this is one of the new slides that I posted as new slides title. We can change the rate of our nucleophilic ring, or change the rate of our reaction by adjusting the nucleophilicity of the ring. So what we'll do is put on an atom X. In our top case, atom X has more electrons than the hydrogen atom. Our hydrogen is our baseline, our 0 point. Okay, and we'll compare everything back to that hydrogen. So we look at that first atom bound to the ring. If it has more electrons than a hydrogen, we can then classify it as an activator and a para-ortho director. Why do we know we can classify it as an activator? Draw the resonance structures of that starting material. What happens? You see negative charge put at the ortho and para positions. If we have negative charge there, we've now made a better nucleophile. So it's an activator. How do we know it's a para-ortho director? The para-ortho director, I would argue that you can look at just the starting material resonance. Officially, that's not the correct answer. You would have to go and look at the sigma structures. So you'd look at the sigma structures for your para or ortho versus your meta. And you would see that the para and ortho substitutions give you more resonance structures in your intermediate. More resonance means more stable, and you're better off. Okay? Why do I say para-ortho and not ortho-para? Which one substitutes? So if we've got an activator, we've got negative charge at the ortho and para positions, which means both of those positions can potentially react with our electrophile. Where does our electrophile go?
Usually to the para.
Why usually to the para?
Because with ortho, you've got two electron-containing groups next to each other. Para, they're opposite sides of the ring.
If we look at our ortho, so we start from that very beginning structure, and I guess I'll show it in blue. If we take that double bond and try and move it out towards our electrophile, we're moving electrons, right? Those electrons have to pass by what? More electrons. What happens when they get near each other? Repels, and those electrons tend to sit at that position. Whereas if we take a look at the para bond, what does it have to get by?
Just the hydrogen.
Hydrogen, relatively few electrons. So what argument are we using to say that the para is more likely to be substituted than the ortho?
Steric hindrance.
Steric hindrance. So there's two big answers with everything organic. Resonance is the big one. That got us to our para and ortho positions. The next big answer, steric hindrance. Okay? So the larger your X group is, the less likely that you will see the ortho position. Okay? Or the larger it is, the more likely you see the para. Okay? Because that steric blocking prevents that substitution. Okay? What happens if we go through and now change atom X and we make atom X positively charged? Okay, so the positive is our big red flag. That's our nitro, so our quiz question 3. Really what we're saying is atom X has less electrons than hydrogen. There's only one way to really have less electrons, and that's for it to be positive. Where that becomes tricky is it may not necessarily be a formal positive. It may be a partial positive, as we saw in question 4. How would you determine if it was partial or formal? How do you know it's formally positive?
It says so.
Got the charge on it. How do you know it's partially positive?
Resonance structure.
Resonance. How do you know you have resonance? Freaking draw the structure. Okay? So atom X has less electrons than hydrogen. We could now go through and look at the resonance of that species and try and see what charges build on it. You'll notice that we still build charge at the ortho and para positions. However, what happens to that charge in these cases? That charge is now positive. If our ring is lacking in electrons, can it act as a nucleophile? Nope, that's the complete opposite of the definition of a nucleophile, which means we would expect that reaction to go slower. Slower downer was apparently already taken, so they picked deactivator as the name. Okay. How do we decide that it's a meta-director? You draw out all of the sigma structures for your ortho, para, and meta positions, and you notice that the para and your meta position, your ortho and para will put positive charges near each other. So we negate one of the resonance structures in our sigma intermediates. Okay? So that means our para and ortho can't react. The only position left over is our meta. Which meta do we react? Is there a difference between the metas in this case? No. So which one? Doesn't matter. Pick whichever one you want. Okay? All of the different structures that you will see can all be applied back to this. Okay? Nitro is a good favorite because when we draw out the nitro, draw it up here, one of the things that you'll typically see me do when I do the nitro is to put on all of the lone pairs on it. Because what's the gut instinct when you take a look at that? Look at all of those electrons. It must be an activator because it has lots of electrons. Are those oxygens with the electrons atom X? No. Evaluate the first atom bound to the ring and decide what its charge is. It's going to be what determines whether you're an activator or deactivator. Okay? So don't get misled by seeing other random weird stuff floating out on the periphery. Focus in only on atom X, address everything else after that. Okay? Yeah.
What if we're doing NO2, but like it's drawn out where there's double bonds, less neutral, should we?
It won't be drawn out like that. Nope. What's the problem with that? Yeah. Nitrogen now is pentavalent, can't do that. So it'll never be drawn out like that. Unless the question is, what is wrong with this structure? Okay. Other questions? Okay. So what we'll now do is give you another example. I like to call these the was or whans. Whans sounds more fun. If we take our benzene ring, and now I'm going to put on bromine. We've got our definitions. What's atom X? Bromine. Does bromine have more electrons than hydrogen? Yes. What does that mean bromine should act as? Activator. Anybody have any problems with bromine sharing electrons with our carbon? Why does bromine have a problem with it? I agree. It's more electronegative than carbon. Okay, we could take it even further. Can bromine actually have two bonds? No. Okay, so we would say, yeah, it may have more electrons, but bromine is electron withdrawing. It's going to draw electron density away from the ring. So we end up with kind of an issue with our halogens, and it works for all halogens. We have an atom that has more electrons than hydrogen, but it's not willing to share those electrons. If anything, it actually draws the electron density away. So what do we classify our halogens as?
Deactivators.
They turn out to be deactivators. But if it's a deactivator, where does it direct? It directs to the meta position. Where do our halogens direct? They go to the para-ortho positions. Okay? Our halogens are the one weird exception when it comes to dealing with your nucleophile chemistry. They're a blend of both deactivators and para-ortho directors. They split that difference. Okay? I don't want to go into it any more detail than that, but if you want more discussions, it's looking at the electrons on the bromine. Okay? Those are effectively in a pseudo-overlapping p orbital, which puts a little bit more electron density at the para and ortho positions. Okay? It's a weird example. Okay? So you now have the abilities to do virtually all EAS reactions. Okay? You know how to address the nucleophile. You know what all your electrophiles are. It's now just a question of putting them on and just moving forward with the problem. Okay? One caveat with that. What if you have multiple substituents? I thought it was supposed to stepwise. So much for that. First problem. What's our electrophile? What are we putting onto our ring? We're going to put on bromine. Man. Where does the CH3 direct?
Oh, ortho.
Our CH3 will activate our ortho and para positions. Okay? Can we put the bromine at the para position? Nope. Why? There's no hydrogens. EAS is all about substituting hydrogens. Okay? So let's take a look at our one option would then be we'd put our bromine at our ortho position, one of those ortho positions. But there's two substituents here. We also have the nitrogen. Where does that nitrogen direct?
Meta.
How do you know it's meta? I don't see a positive charge on that nitrogen. You're right.
But we already just
Still
did
there.
it.
It's not listed.
The one way where it might be hidden on your nitros, they might specify it as NO2. It is referring still to that positively charged species. Okay? Where does the nitro direct? Meta positions. Hey, look at that. Okay? In this case, everything directed out perfectly. Where would we expect to put our bromine? Either side of our CH3. Whoops, it should be bromine, not nitrogen. Okay. What happens if instead we started with this species? Same reagent. Put on our Br+. Where does the CH3 direct? We've got our para and ortho positions. Where's the nitro direct? To our meta positions. What's the problem with this? Okay. We've now come up with a way to show somewhere on this ring, or that every hydrogen on this ring has the potential to react. Because we've colored all of them in. Okay, so which position does react?
How about the ortho that's opposite of the nitro group?
I would probably put it over here. Whoops. There is one other likely option. Whoa, that was a lot bigger than I thought it was. The other likely option is putting it over here. Why do I not draw the third one? Because there's that third position. Steric hindrance is going to block that other one. Why did I pick these two and not the blue ones? You'll notice that we put the bromines at our red positions.
Well, the methyl group is an activator, methyl group is a deactivator.
So what does that mean as far as our chemistry goes?
It goes faster with the methyl.
Activators trump deactivators. Okay, so one of the first lessons that we can learn is that if we have an activator and deactivator on our ring, the activator is going to determine where on that ring it's going to go. Okay? What happens in the next case? What's the issue in the next problem? One under erase. What's the issue in the next one?
They're both para-activated.
They are both orthopara activators. Our oxygen is going to direct to those positions, and our methyl is going to direct to those positions. Okay, we've got a similar issue here. Okay, both the position where our oxygen and our carbon are won't react. Okay, but we've now shown that all the other hydrogens have potential to react. So what's the result? What do we end up seeing? What's that? Why ortho to the alcohol? Yes, there's your rule. Okay. Not only do activators trump deactivators, but stronger activators trump weaker activators. The oxygen is a stronger activator than the methyl. Why? Oxygen has lone pairs, the carbon does not. Okay? So we've got a couple extra rules when dealing with multiple substituents. Okay? You need to start off with your activator trumping your deactivator, and then your stronger activator trumps your weaker deactivators. You need to be able to process in that fashion. You can get multiple products. That is a possibility. Usually, or at least on the test, we'll definitely be pushing towards one product being our primary. Okay? Sapling might have you draw out multiples. I don't know about that. Okay? What happens in these cases? What would our products be? What's our electrophile? We've got NO2 for both of these, right? Yeah. What do we expect to happen in these cases? Why is this one or these ones more difficult of a problem? I don't know why I'm drawing these all out, because I think I've got them on there. Any ideas why they might be more of a problem? Which one's the stronger activator? They're pretty similar. We might say that isopropyl is a little bit stronger because it has more electrons, but you're running into some pretty gray areas there. Okay, so these are effectively the same activating, deactivating positions, or activating abilities, which means
Does it just come down to steric hindrance then?
it's going to come down to steric hindrance on deciding where to put our nitros. So we could expect to put our nitro out over here or out over here, which should be the same. We might also see one close to our isopropyl. Okay. Likelihood that we put something closer to the isopropyl, not so much because the isopropyl is bigger. Okay. It's going to sterically prevent those positions. What happens with the next one?
Go like one pair to the methyl group, the bottom right there.
The next one's a little bit easier. Whoops, I shouldn't do it on that one. Because the ortho positions, okay, so we could look at both of these being sterically blocked, so we wouldn't expect those. Okay. Whoops, why did I highlight that one? That one shouldn't be highlighted. Which really leaves us only with the option of putting it out there, okay, as our primary option. Okay, so it's a question of evaluating the directing effects of each of them. It may not be a bad idea to bring in different colors to try and match those up and see what happens. So we would expect our higher yield for that next one to be putting our nitro down at that end. Okay. And with the top one, they're identical, so I don't know why I asked the higher yield there. Okay. We could see that other nitro there, so this is why I said the higher yield, because of what the textbook threw on it. Which of those two would we expect our higher yield to be? Left or right? Left because, whoops, sorry. Left because of the steric hindrance between the nitro and the isopropyl. For the other one, bottom one, which side would we expect? Oh, that's kind of boring. Still left. Again, steric hindrance. Okay.
So you see with it, since they both, you see which positions they both activate and see
Yep.
which ones.
And then evaluate from there. So when we did 1 and 2, effectively what we're doing is deciding which positions are activated, our para or our ortho positions. Okay? And both question 1 and 2, both of them, we should have said para. Okay? Why do we say the para over the ortho? Well, there's no resonance argument. Both of them are equally activated. That's where we have to refine our definition a little bit further, and that's where we jump in and say, oh, steric hindrance. Okay? The steric hindrance is going to limit the ortho. We favor the para position. So you'll see the textbook. I think textbook typically refers to it as ortho-para directors. I'm trying my hardest to always refer to them as para-ortho directors because para is the more likely position in those cases. Okay. Questions about that? Okay. We just talked about that summary. Okay. I don't know why I brought it up earlier, but I did. So this summary did come from your textbook, so you do have access to this. Kind of nice to summarize all of your EAS reactions, and I'm pretty sure actually all of the reactions that you saw in chapter 18 too. Okay, the only one we really talked about there was the chromic acid and their permanganate. We mentioned the Birch reduction. Okay, so if we were going to make this slide an overall summary of everything, remember we've got that Birch. I think that's right. Our Birch reduction. What did that do with our benzene ring? It reduces it, which means, what do we need to add to our structure? Hydrogens. So we get our double bonds on opposite sides, and the reagent. So that would be a standard idea, our H2. H2 in platinum doesn't work. We did use something else. Nope. It's the sodium, metal, ammonia, and I think we also had an alcohol, maybe methanol. Okay, those were your reagents for your Birch reduction.
Did the H2 and the nickel or something like that get rid of all of the
Oh, yeah, I see what you're saying. If you wanted to really, really reduce it down, the issue with that was that required really high pressures and really high temperatures. So we typically don't use that as a reaction. Whereas our Birch reduction is a very selective, I guess it's selective, to reduce just one double bond as opposed to all of them. So yeah, I see what you're talking about. So we do have a standard reduction of everything, but that's a lot more work. All right. As far as a question about that full reduction on the test, probably all I would ask would be, is that heat of hydrogenation really high? Yeah, it's really high. Okay. So our steric directing effects, reversibility. So if we take a look at that starting material, if we want to put bromine, what reagent should we use? What reagent gives us an electrophile of Br? Br2, and we could add in the FeBr3. If we use that reagent, where should we put the bromine? Ortho, well, be careful with the terminology. I want to say para-ortho. Between those two, which one is favored? The para, because the steric hindrance, and we've got a lot of steric hindrance with that T-butyl group at our ortho positions. So if I actually want to obtain that product with the bromine at the ortho position, bromine in FeBr3 isn't going to work. Okay? Could I potentially block the para position to prevent the bromine from going on? So I could do an extra step where I put on some kind of blocker. And if I did that, then the ortho has to react. But what's the issue with the blocker? Take a look at our product. Do you see blocker there? No. So we need something that is a reversible process. What's our reversible reagent? Our sulfate group, our H2SO4. Okay? So we could go through did I want that one? Oh, yeah, okay. Sorry, I thought I was expecting a different slide. We could put in our H2SO4 fuming to put on our blocking group. Then we could do our bromine with our iron tribromide catalyst. And then we can remove our H2SO4, or sorry, our sulfate group by doing sulfuric acid and dilute. Okay? And that gets us to that actual product. Okay? So sometimes you have to travel away from your product before you can actually get back to it to get those proper substitution patterns. Okay? How would we get that last one? What different reagents do we need to use?
Nitric acid.
NO3 and H2SO4. Okay, we want to use our alkylating reagent, or sorry, acylating reagent, which will be our, make sure we get the correct number of carbons, 1, 2, 3. And we need a good leaving group with our aluminum trichloride. And then we need our bromine, our Br2 and FeBr3. Does it matter the order that we put these on? Probably. Good call. Where does the nitro direct? Let's assume we put the nitro on first.
Meta.
That directs to the meta. That bromine is ortho. That seems a bit questionable. Okay. Not only that, but what does the nitro group do to our ring? Deactivate it. We're not going to get high yield if we put the nitro on first. Okay, so let's put the acyl group on. Where does the acyl group direct? Meta again, we got the para-ortho. Or sorry, our bromine is para. Okay, so that could have been a nice idea to get the nitro, but then we're still stuck with this bromine that we can't put on into the para position. Okay, what's the last option? Put the bromine on first. Where does that now direct?
Para.
Our ortho para position, so we can start with our bromine, which now activates deactivates the ring, but mildly in comparison to the other two, and gives us our orthopara substitution. Which one do we now put on?
The acyl,
Why the acyl?
because the NO2 is going to have a positive charge, whereas the acyl is just going to positive one.
And what you're addressing there is that the nitro is going to deactivate the ring a lot, which is going to reduce our yield. Whereas the acyl group, when it goes on, okay, doesn't deactivate the ring quite as much. Okay, there's another good reason why we should put the acyl on first. Wait, I just forgot what it was. Yeah, sorry. Yeah, no, I forgot what it was. So yeah, let's just stick with that. Good reasoning. So that leaves us with our last option, putting on our nitro. Okay. So just identifying the reagents gets you partway there, but it turns out you have to put them on in the proper order. You put them on out of order, you get a different product, or you don't get the product at all. Okay. So Sapling will definitely test you on those. You should have a whole bunch of questions along those lines. Okay. Yeah, as far as Sapling goes, I think I got it set up to do 3 two-step reactions, 2 3-step, 2 4-step, and 2 5-step reactions. Okay, as far as the homework goes, just so you're aware. Okay. So look for those pieces, identify the reagents that you need to put on those individual pieces, and then start trying to process it like a puzzle. If we put this piece in first, what happens? Whoops, try a different piece. Okay? Questions?
Should we expect more than 3 steps?
No. Yeah, the 5 steps are there just as practice. Get you kind of used to playing with the reagents. So now we run into an interesting question with the very end of the chapter. We end up with what's known as the nucleophilic aromatic substitution reaction. Okay, so what happened in this reaction? What bond was broken? What bond was made? What was that? Broke the carbon-bromine bond and made our carbon-oxygen. Interesting. That looks an awful lot like just a substitution reaction, which if we go back to your substitution chapter, what did we say about substitution reactions happening on aromatic rings? They don't. So why on earth would we now show you a case where it does? That's because it's a very particular circumstance. Okay, what's so special about this reaction? Okay, we got a reasonable amount of heat. We still have a nucleophile. What else is special about this? We're adding a base or a nucleophile, right? Okay, it ultimately needs to act as a nucleophile. For this reaction to work, what charge does our carbon need to be? It needs to be positive. Is it partially positive? Okay. Well, what we taught you before is if we just had bromobenzene, that partial positive did not react. What's different about this versus standard bromobenzene? The NO2. What's special about that NO2 down there? Why is it deactivating? Pulls electron density out of the ring. What happens to that carbon? We can generate a full formal positive charge on that carbon. Okay? So if we start with a very deactivated ring, yes, we can push the substitution reaction. Okay? Is that an extra layer of difficulty to it? Yes, which is exactly why we didn't teach you that first. Okay? So we start with our alkyl halides and just say aromatics don't react. As a general rule, that's true. If we vastly deactivate the ring, we can get it to react. Okay? And so it comes back to dealing with that mechanism. That electron density siphons back away from it. Our OH minus can then come in and attack our carbocation or our position we can kick out our bromine or our bromide as the leaving group. You'll notice that step 2 is to add H3O+. Why do we have to add H3O+? Why do we have to add an H? Didn't our OH come in with an H?
But the bromine needs to leave with one.
No, bromine's not going to leave with one.
Or sit in solution with one.
What functional group is this? Phenol, what's special about the phenol chemistry? It's an acid. What species did we add in step 1? A base. What happens as soon as we do the substitution? That hydrogen is acidic and gets removed, and we end up with the phenoxide. How do we get our phenol product? We have to add a hydrogen by adding our H3O+. Okay? So in the case of the nucleophilic aromatic substitution, we are bringing in a nucleophile, and it has to be a pretty strong nucleophile to do this because our aromatic ring already has electron density in it. Okay? So we need a good strong nucleophile, and we need a deactivated ring to cause it to occur as well. Okay, is there anything else that we might need? Say, let's look at another reaction. Virtually the same reagent, bromine and nitro on our ring. Same compounds that we add into it, sodium hydroxide, temperature, a little bit of acid, and our result, nothing. Why do we not get a reaction in this case? Okay, the position is a deactivator. Yeah, why does that matter? Why did we say in the first case it did work? What was the charge that built on our carbon? We were able to put a formal positive charge on that through resonance. So let's see what happens if we try and do resonance with our other one. So our first arrow would put positive charge here. Second one puts positive charge there. Third one puts positive charge there. Do we have a leaving group at any one of those carbocation positions? Nope. No leaving group. Can we do a substitution? Nope. That's why it doesn't work.
And none of that would react. Replace hydrogen. Do an EAS.
So an EAS would be a different reaction. Then what does our aromatic ring need to react with? An electrophile. Is sodium hydroxide an electrophile? Nope. So we do have the potential with that, what is that, meta-bromonitrobenzene, to do an EAS reaction. But the reagent we're adding here, not an electrophile. So we can't get that reaction to occur under any mechanism. All right, or under either mechanism, I should say, in this case. Okay? So with our NAS reactions, we need to have an electron poor or deactivated ring. So nitros are big signifiers that you're probably pushing an NAS reaction. So we're looking at a strong electron withdrawing group. We need a good leaving group, so we're going to have to look for that halogen. And we need to have that halogen located at the ortho or para positions to our withdrawing group. Why? So we can get our resonance stabilized carbocation to allow for our reaction to actually occur. Okay? So those are going to be the rules that we're going to have to watch for when we're dealing with our NAS reactions. If we were going to try and decide if we had an NAS reaction versus an EAS, okay, what could you look for to help you decide between those? What would you tell me about the reagents? Okay, what charge would you expect to see for a nucleophilic reagent? Negative. So if you look at your reagents and you see a negative charge in there, what is that going to mean? You're looking at an NAS type mechanism. If you look at it and you see positive charge, Bronsted-Lowry acids, Lewis acids, you're now looking at an EAS reaction to get that electrophilic species. So just because you have an aromatic ring does not mean you will always push the EAS reaction. You do have the potential for the NAS. Okay? The NAS also requires that kind of higher heat to help kind of initiate this and get this going. Yeah?
So you couldn't do an NAS with like a carbonyl attached, right? There have to be something to be a formal positive, not just a.
I was
strong
hoping you weren't
partial.
going to ask that. I'm not positive how strong the withdrawing group needs to be. All of the examples I've seen have been nitros to get the NAS mechanism. There's another mechanism that we'll look at here in a second. So I'd have to make reference back to the textbook and see what they say on it. Why do I not know a whole lot about it? How commonly do we use NAS mechanisms? Very, very rare. Most of the mechanisms you'll see will be EAS. Okay, so that's why I just don't know as much about it. Okay.
But it's not something we're going to have to decide between that.
No, I'll probably stick to the nitro groups. As far as the sapling homework goes, I don't remember, but I think they stick with the nitro groups too. I think you do need that formal positive nitrogen. You really need a strong electron withdrawing group. If you look at the textbook, someone's got it, you should be able to flip through, and I think they rank the substituents according to activating, deactivating, or electron donating versus electron withdrawing. And they say this is weak, this is strong. If they aren't specifying it here in the slides, it better fit in that strong category. The nitro for sure is in that category. I don't know about the other ones.
For NAS, you would need a deactivating group.
You need that deactivating group to push that mechanism. Okay. Other questions on it? Turns out there's another one we can get. If we ran through and did this circumstance, okay, so we took chlorobenzene, so a halobenzene, just like we had before, did our sodium hydroxide, and the slides are, I can't tell if it's intentional or not, vague as far as what they're specifying heat. Let's say the heat is 70 degrees in this case. So the same as we saw for our NAS mechanisms. What we would predict is no reaction. And sure enough, we get no reaction. Okay? Then somebody decided to get crazy, and probably for a different reaction that they were trying to run, they added sodium hydroxide, and they did significantly harsher conditions. They jumped up to 350 degrees Celsius. And what they ended up seeing was that they did get the substitution. Okay, well, that seems really odd. According to our NAS mechanism, okay, we need that electron withdrawing group to activate it and allow the reaction to occur. So something else must be going on in this case. So they went through and tried to derive different reaction conditions to see what that mechanism might be. And after all of those conclusions, we end up with a very odd result. Okay? That result is this elimination addition mechanism. If we eliminate, what are we making? All elimination reactions result in the formation of a pi bond. So you're right as far as thinking alkene, but let's take it in a broader stroke, pi bonds. Okay, so if we do an elimination reaction on our aromatic ring, what would happen? Where would we eliminate? What for sure would have to get eliminated in this reaction? Chlorine would have to leave, so it would take electrons. To do an elimination, though, we have to remove something else. What do? We remove a hydrogen. So we take the electrons away from the hydrogen to form our pi bond. Okay? How can we break that carbon-hydrogen bond? What is our aromatic ring acting as? An acid. So what do we react acids with? Base. So if we react it with a base, like sodium hydroxide, that can help facilitate the elimination reaction. What's the result of an elimination reaction with a benzene ring? Right? Did we touch any of the sigma structure? No. Did we touch the pi bond to the far left? Actually, did we touch any of the pi bonds in the ring? No. We added a pi bond. What? Yeah, really, really, really weird. We end up forming a structure known as a benzyne. Okay? We do form a triple bond within the ring. How would we be able to predict that this actually formed? Okay, well, we have an electron-rich source here that really doesn't want to have all that electron density there, And that pi bond is going to want to break and share with something. Have we seen a reaction, say maybe in lab primarily, where we had a pi bond react with something else? What did it react with? This is a single double bond. Tends to react with this is a dienophile. We can react it with a diene. The aromatic ring, due to the pi bond structure, or the resonance within the aromatic ring, would not react in a Diels-Alder reaction. If we formed the triple bond, is that pi bond now ridiculously high in energy? Absolutely. We've now changed the aromatic structure, and we now have an active reactive pi bond. If it is indeed present in the compound, or as an intermediate, if we add in a diene, we would expect the Diels-Alder reaction. So, sure enough, they took your chlorobenzene, added some base to it, and then threw in a diene just to see what would happen. What happened? They got a Diels-Alder reaction, which meant that they had to have formed the benzyne. We needed to form that triple bond. As weird as that structure may be, it does exist, and there is proof and evidence that it is there. So it's kind of neat in that respect. Okay? So, actually, let's take a step back there. The big difference that you're looking for here are really, really harsh conditions. You're upping the temperature significantly. We aren't looking at kind of mild, boiling water stuff. We're looking at kind of melt your face off temperatures. Okay? You're jumping up into close to burning book level, right? Isn't it 451 Fahrenheit? 450? Oh, that's Fahrenheit. Anybody know what 451 is in Celsius? Can't do that conversion. That's probably really, really hot, probably burning book level. Okay? So you're looking at extreme conditions to get this reaction to occur. Another piece of evidence that would suggest this works, that we're getting that elimination, is what happens if we add a stronger base. Well, to do the elimination, we need a base. What happens if we increase the strength of the base? We would expect the reaction to go faster. So what happens? They went through and tested that as well. And if we use a stronger base, such as sodium amide, we see that mechanism, or we see that substitution occur at a much better rate, slightly more mild conditions to get that reaction to occur. And by slightly more mild, if that's really liquid at room temperature, that's really mild. Because ammonia is a gas, right? Turn that into a liquid, you're looking at pretty cold temperatures. Okay? Why is amide a stronger base, or a stronger nucleophile, and for that matter base, than hydroxide? What's the difference between nitrogen and oxygen? Electronegativity. Nitrogen is less electronegative than oxygen, meaning that it is more willing to give up those electrons, both to a hydrogen and towards an electrophile. Okay? So we've got our elimination addition reactions. If we put on different substituents, we're also going to see some regiochemical explanations, and we can't really match that up based on what we've seen so far. Okay, so that's another reason why we need the alkyne. Why would we see both of these results? Well, if we do the elimination, what's our intermediate look like? We will end on this. Ooh, I don't have a lot of space in here. Oh, and that's not a good way to draw it. I have to turn it sideways. We'd get our benzyne out there. Which carbon reacts in the benzyne? In any addition reaction, which carbon reacts? Which one is the stronger nucleophile? The least substituted is our nucleophile. Which position is least substituted? They're the same, which means what happens when we see it react? They both react, and we can see our substitution occurring at both positions. Okay. So our elimination addition reaction does generate these two products, and that's a big piece of evidence again for that benzyne formation. Okay. Not sure where we are with slides. So this is actually breaking down the mechanism a little bit slower. So in that very first step, what are we doing? First step down here, what are we doing? Would be the first step of an elimination reaction. Okay, technically, well, actually we can't even call that an E1 because E1, so it would be a cation. So it's our first step of our elimination. We could also classify it as what type of reaction? Not that first step. We took a proton, it's the transfer of a hydrogen. It's an acid-base reaction. Next step of the reaction would be the second step of our elimination to generate our benzyne. That benzyne then goes through an addition reaction at the very last portion of it. Shoot, didn't say that. And we can do our addition mechanism to get our final products. Okay. Adding both hydrogen, where's the hydrogen coming from? The ammonia solvent, so our NH3. And the NH2 goes in to stabilize the other carbocation. Okay? Textbook goes through and explains some other things with it. You can look at it as a diradical instead of a benzyne. They're showing some more mechanistic steps, which we've already seen. It's how that individual attack can occur, which we just addressed. Here's our Diels-Alder evidence as well. So I jumped the gun, talked about the Diels-Alder a little bit too early. So if we have that benzyne, we now have a reactive pi bond. We would expect that to react in a Diels-Alder reaction. So sure enough, they tried to form the benzyne using the strong base in your benzene structure and then threw in a diene. Sure enough, we saw that addition reaction when we could confirm that we had that product. Okay? Oh, and there you go. So that is chapter 18 and 19. Went a little bit over today, but not by much.